Okay, this is chapter 15, part 2, lecture 2, part 3. So we want to talk a little bit here about selective precipitation. Now, this overall idea relies on the principle that if you have a low, a small KSP, maybe is the better vocabulary word to use here, it means the substance is less soluble. Okay, so as an example, let's say I have a test tube that contains in here 0.1 molar copper ion and 0.1 molar nickel 2 ion, okay? And I want to add hydroxide ions to this, okay? Excess, and I'm adding it dropwise and so on. And I'm wondering what is going to precipitate first. I know that this reaction could happen. Copper 2 plus can react with 2 hydroxide ions to give copper hydroxide. I know this reaction could occur. Nickel could react with 2 hydroxide ions to give nickel hydroxide. Okay? And what we want to do is think about the KSP values here. Okay? So copper hydroxide, let's say, has a value of 2 times 10 to the minus 16, and the KSP for nickel hydroxide, let's pretend, has a value of 2 times 10 to the minus 31. From these data, we can make the conclusion that nickel hydroxide is less soluble and will precipitate out first. Okay? And so what our test tube would look like afterwards, if we did it very carefully and correctly and tried to stop at this stage, you would have a precipitate on the bottom, and that precipitate should be nickel hydroxide. And up above, you would have still your copper ion. Okay? And this would be something that would be easy to be demonstrated because copper is blue and nickel is green, so you have like an aqua color here. And then if copper remained behind, this would be a blue, a blue color, and you'd have a green precipitate on the bottom. It's kind of an interesting thing. Okay? So in the lecture guide here, we have an example. It's more of a question. We have a mixture of 0.1 molar silver nitrate and 0.1 molar iron nitrate. How could you separate these two? Okay. Now you might be thinking, well, we'll add hydroxide just like my example, and I could make silver hydroxide precipitate out, and I could make iron hydroxide precipitate out, and I could find out what the KSPs are and compare them and see which one's solid or not. Well, what I suggest you do is actually use chloride. Chloride would be even better because chloride forms an insoluble salt with silver ion, but iron chloride would be completely aqueous. Okay, so this guy here would be a solid. This guy would be aqueous. So then what you could do is you could take your reaction mixture and you could pour it in through a funnel that has a filter. And you could pour your liquid in here. What would pass through the filter is your aqueous iron chloride. And what would be trapped on top of the filter would be silver chloride solid. So that's how you would separate the two. I mean, you wouldn't get silver nitrate and iron nitrate back again. You would have two different chemicals. You'd have silver chloride, which is something different, and iron chloride. Okay? So here's another example that you might like to try. How would you precipitate, or how would you separate .1 molar barium chloride and magnesium chloride? Okay, another one. How would you separate .1 molar copper chloride and .1 molar iron 3 chloride? Okay. So I'm specifically looking for what substance would you use? Not necessarily the whole experimental procedure, but just what formula would you use to separate? Okay. What precipitates out first? What would remain aqueous? That would give me a clue as to what you're going to be filtering and what you're going to get in the aqueous mixture at the end. Okay. Let's keep going here. We want to talk about solubility in acids. Okay. So let's talk a little bit about copper oxide. Copper oxide is a brown coating that exists on, old pennies. And one of the classic, second grade, third grade, fourth grade type of science projects is to take pennies and try to clean them with vinegar and lemon juice and things like that. The chemical reaction that occurs is that the acid from the lemon juice, for example, will cause copper oxide to be more soluble and produce soluble copper ions, which can be washed away or absorbed by a paper towel or something like that. So if you increase the acid, this reaction will shift right, and you'll make the ugly brown pennies shiny. A stronger acid also works better because it has more H plus in solution. And so what students find is that the strongest acid, I think lemon juice works a lot better than, vinegar or something like that. Okay? And this idea is all due to Le Chatelier's principle. You shift away from the decrease, okay? Copper oxide is not soluble by any stretch of the imagination. If you throw in a brown, dirty penny into pure water, it just doesn't clean up, okay? So strong acids will do the job. And this is how you clean pennies. So you're practical lesson here is that you can clean a penny with hydrochloric acid or something like that. All right, let's look at another example, calcium carbonate. We know calcium carbonate is an insoluble substance. It's chalk, it's limestone. And it can form calcium ions, and it can form carbonate ions. Okay? And so how can we cause this reaction to shift to the right? You might be thinking, well, we need to decrease the concentration of calcium ion, or we need to decrease the calcium of carbonate. Okay, and that's what we want to do. We want to lower the carbonate concentration to shift this to the right. And we do that by adding acid. If you take carbonate and you add H plus to this, you will get bicarbonate. Okay? This is the KSP. This is the KB for carbonate. If you take equation 1 and you take equation 2 and you add them up together, you will see how carbonate cancels from both of these equations, and you get a net chemical equation that looks like this. Calcium carbonate plus H plus is in equilibrium with calcium ion concentration and bicarbonate ion concentration. Okay, and the equilibrium constant for this one, we apply the product rule, is going to be the KSP times the KB. And we've looked at these rules of equilibrium before. And so now if we look at this chemical equilibrium, it's very clearly evident that we can do a couple of things, okay? If you increase the concentration of acid, this reaction shifts right, okay? Two everyday applications of this are coral in the oceans of the world. As corals dissolve, as seawater acidifies due to global climate change, okay? Now you might be wondering, well, how does the seawater get acidic? I don't understand that. Well, carbon dioxide from coal burning and oil burning power plants, cars, and all the global activity of humans reacts with water to give you carbonic acid. Carbonic acid can dissociate to give you H plus and bicarbonate. Okay, and this H plus, well, I have the equation up here. The H plus will then dissolve, corals. I'm not sure how to spell that. I think it's with one L. Corals, okay? Another application of this is caves. For example, Roanoke, there's a lot of caves. There's limestone. Limestone reacts with groundwater that might be acidic. So limestone, as we mentioned, is calcium carbonate, and acidic groundwater that passes through the ground contains a little bit of acid, and this will dissolve calcium carbonate slowly over hundreds of years to create large caverns and openings and caves and so on. Okay. So what do we have here? Let's go back and review, because you might be falling asleep. Metal oxides dissolve in acid. Metal carbonates dissolve in acids. And the last thing here is metal hydroxides dissolve in acids. So if we have an example here, nickel hydroxide is a solid, It reacts with 2H plus to give you nickel ion and 2 molecules of water. Okay, so if you add H plus, you'll dissolve this nickel hydroxide. So we know the KSP for nickel hydroxide and what do we do to this equation in green to make it look like that? Okay. One thing we could do is write out the kW for water. So H2O, which is a liquid, is in equilibrium with H plus aqueous and hydroxide. Okay, and that has a value of kW. Now, water in white is over here, water in green is on the left over here. So let's flip this. We'll now have H plus aqueous plus OH minus aqueous in equilibrium with H2O liquid. Okay, so that equilibrium constant is going to be 1 over kW. So now we have water on the right and water on the right. Okay. And let's see. Well, to get these two equations, this one here and this flipped equation here to cancel, we're going to need to adjust the number of hydroxides. There's 2 hydroxides here, and there's only 1 hydroxide here. So what we're going to do is multiply this flipped equation by 2. So we're going to change this to 2H plus 2 hydroxides in equilibrium with 2 water molecules. And remember what we do to the equilibrium constant, we square that. Now I can take this, let's change back to white, I can take this starred equation, I'm sorry, not that one. We can take this KSP equation here in green and add this equation together to get the net. Okay, so I'm going to take the star and add the star together, and I'm going to get nickel hydroxide plus 2H plus aqueous plus 2OH minus aqueous. And that's all going to be in equilibrium with nickel ion aqueous, 2 hydroxide ions aqueous, and 2 waters. Okay, and you can see how the OH minus on the left and the OH minus on the right cancel out. And the net reaction there is the one that's shown on your lecture guide on page 41. Okay, and we use the product rule. The value for this equilibrium constant here, this equation in green, this really long one here, is going to be equal to the equation 1 times the equation 2, which I said was 1 over kW squared. So I could look those values up. I know what kW is, but I don't memorize the KSP, and I could compute this and get a number for that. Okay. So I have a Keurig, coffee maker at my house, and every once in a while, every couple of months or something like that, it pops up and says you need to descale the, the coffee maker, and you need to go on YouTube and see how to do that. But normally you do that with vinegar. So let me point out the you try it problem. Calcium carbonate is responsible for all these spots on glasses as they come out of dishwashers and scale that builds up in your coffee pot and things like that. And we know what the KSP is. It's, calcium ion and carbonate. Okay? And we know that vinegar can clean this calcium carbonate off. It can dissolve it and make it new again. How does that work? Vinegar is this substance here. That's a liquid I'm trying to put in here. I'm sorry, it's aqueous, right? I'm thinking how badly I would benefit from some coffee. All right, so aqueous forms H plus and carbonate. Okay, so this is, we call this the KSP. What do we call this? Is that the KA, the KB, the K something? And we need to manipulate these somehow. There's going to be a balanced chemical equation that shows how calcium carbonate can be dissolved with acid. So what's the net equation? Of calcium carbonate reacting with just 1 molar equivalent of vinegar to give bicarbonate. Okay, and what is the K for that process? Okay, you might have to apply the rules of equilibrium to determine what that is. All right, this, I believe, summarizes up to this point. If I have some YouTube videos, I'll link them into the Canvas website. Otherwise, I won't be making more YouTube videos. I suggest reading the OpenStax book for more examples, more problems. And this concludes Chapter 15 in terms of the equilibrium solubility products. There will be a couple of videos on equilibrium in this following. Okay.